What up, and we're back with word problems. What happens when your sheep get out of their pen? Oh man, let's find out. Just like they come up to your sliding glass door and they're like, let me in. I'm like, just go eat grass. Just go eat some grass. Yeah, thanks for watching. Woo! So doing word problems today. Word problems. Oh, word problems. Okay, so we did graphing logarithms last time, so hopefully you aced that part of the assignment. And now we're doing exponential growth and decay. I'm doing word problems. And so not as bad as you think. At first it was a bit intimidating to me, and then I kind of worked it out with the help of Miss Coher, Lucarini, Barney. Thanks for your help. You gave me some good guided notes to help me. Okay, so exponential growth and decay word problems. So the exponential growth forms. This is the fourth form you kind of want to memorize, and how it just works for all of these problems, right? And so you have your initial, whatever they give you. So your initial there, the initial amount of bacteria or people or whatever, and then times whatever your rate is your initial rate that they give you. Nice. And then to the time. Nice. Awesome. And so you kind of have to work with that, and usually you have to do it twice to project onto the next thing that they want you to project. And so another way to look at that could be like this. Here we go. Here we go. Dodo bird. Okay, so y equals a b to the x power, where b is greater than 1. And so what that means basically is that b is going to be greater than 1 because we're talking about growth. So when b is greater than 1, we're talking about growth. Then you guessed it, when b is less than 1, we're talking about decay. So let's do a couple of these examples for you. So you only have 4 problems in the homework. So a scientist started with a culture of 45 bacteria in a dish. The number of bacteria at the end of each successive minute, every minute, is increasing because they multiply like crazy, those evil bacteria. So the number at the end of 1 hour, or 60 minutes, was 900. So it went from 45. So it went from 45 bacteria and then skyrocketed it up to 900 bacteria. And so that's just in 60 minutes. And then they want to know how many hours to the nearest hour from the start of the experiment passed before there were 1 million bacteria, right? 1 million bacteria. Okay, so then how we want to treat this problem is we want to start off with our initial and kind of just plug it into our formula. So we're going to go y is equal to, our initial bacteria is 45. We don't know what the rate is just yet, so we'll just call it b. And then the time period they give us is each 1 minute, right? Just 1 minute, first of all. Then it gets more than that. Awesome. So we have 45 base 1 minute. Cool. And so let's see here. So 45 bacteria. The number of bacteria at the end of each minute increased exponentially. So the number at the end of 1 hour was 900. So let's take a look at our guided notes there real quick. Okay, so then we first have to set that initial. So we went basically from 45 to 900, right? So we're setting it equal to y, which is how far it went. Now we can get our rate. Went from 45 to 900. Well, how many times did it multiply by itself? And so we're going to go ahead and take 900 now, which was this number, and divide it by this number. So 900 divided by 45. And so our rate then is equal to, and so we'll do 900 divided by 45 is 20. Okay, so now we're looking at a rate of 20 bacteria per minute there. Okay. So now that we have that rate, now that'll help us project all the way up to 1 million, right? And so how many hours? So we have our 20 rate per minute, we'll call it per time, equals, and then we're going to go and do 1 million bacteria. That's a lot of bacteria, but it's still probably just a droplet or less. Like, they're so small and sneaky. Stay inside, stay indoors, 6 feet away, social distancing. Oh no, COVID is actually a virus, not bacteria. That's right. Okay, so now we just want to solve. So we have our initial is 20, so that goes here because we solved for it here initially, right? Then we have our initial 45 bacteria in our dish. And so the number at the end of the hour is 9. How many hours is from the start of the experiment? That's why we're not doing 900, we're doing 45, because 45 is the start of the experiment. And so the nearest hour, how many hours have passed before there's 1 million bacteria? So we want to solve this now. This is an exponential solving problem, basically, which we learned about already. So we go ahead and divide by 45. Divide by 45. So let's go ahead and take 1 million bacteria. How many zeros is that? Is it 6? It is 6. Divided by 45 gives us 22,222.22. Lots of twos. That's a lot of fun amount of twos there. There we go. Okay, so there's what that equals. Okay, so then we have 20 to the t power. Now, do you remember how to undo a base and solve for t time? Do you remember? How do you undo a base of 20? Do you remember? Do you remember? Okay, so to undo a base, you have to go to log base. So we are now going to go ahead and log base 20, and then over here, and scientists do this all the time to see how long it's going to take them to grow bacteria. So we're going to go to log base 20. If you do it to one side, you have to do it to the other side. So we're going to log base 20 this number, and so log base 20, that gets rid of it. So this is what t equals now. Nice. So there's our answer. And then we can just plug that into our graphing calculator, or you can even use Desmos or some other online calculator to help you do log base 20 of that number. And so I'm used to graphing calculators, so we'll do that. So you go math button, you go to log base, and we'll do log base 20 of 22,222.222. Okay, there we go. So our answer is, 3 hours, 3 1/3 hours, basically. So 3.34 hours. Cool. That was a fun, tricky problem. That's how long it's going to take. That's not long to go from 45 little bacteria to 1 million. That's crazy, right? They go so fast. So we'll double check that there. And yep, about 3 hours, 3.34. Nice. Okay, so there's only 4 problems in the homework, so that's why we're just doing some examples this time, so you can then practice on the homework. Just a couple problems there. Okay, so then 2 years ago you had $250 in the bank. Now you have $287.50. If the amount of money at the end of each year increases exponentially, how much will you have in the bank after 6 years? Assume that you did not deposit or withdraw any money during that 6 years, just left it in the bank. Okay, so 2 years ago, that's really important, because you're going to have to add that back in when you get to another 6 years, right? So 2 years ago, and then 6 years forward, that's going to be a total of 8 years. So don't forget, there's going to be a tricky part where we're going to have to do that. That kind of tricked me up a little bit, but hopefully we'll help you figure that out. Okay, so you start off with the initial, and so that's right there. So the initial was $250. There we go. So that was our initial, right? Do you remember what you do with initial? So your initial goes in the front. So now we take our $250, which is our initial, and our initial money that we deposited, that goes in front. Then you have your rate that goes here, that we have to solve for first. So this would be the next step, right, is to solve for your rate. Every time, solve for your rate. So that'll be a step in there. So I guess if we were breaking this down into steps, you'd say step number 1, find the initial. Step number 2, use that and solve for the rate, right? Awesome. And so we're going to put 250 here, and then it increases to 287. And so that's what you set it equal to, right? That's what you set it equal to. Your 287.50 goes here, so you set equal to that. And then you divide by 250. Oh, wait a sec, we forgot something. So that's your time, right? So then I guess if we were going to go ahead and say that that was like what, step number 3? So step number 3 would be to put your rate up to the time exponent. Right, up to your time exponent there. Awesome. Okay, so in this case they tell us 2 years is our time. Okay, they tell us 2 years is our time. And so that's actually going to make a difference in this problem because that's 2 years ago is when this happened. And so that means that when we're going to divide by 50 first, divide by 250, divide by 250 to solve for B. Awesome. So then when you do that, you get, let me do some erasing here because I was just figuring out this problem myself. So I could show it to you. There. Awesome. Okay, so we're going to go ahead now and we're going to solve for B. So that would be like step 4, right? So step 4 would be solve for your rate. Okay, so solve for your rate. Solve for B. Okay, there we go. Okay, so to solve for B, we divide 250 to both sides. Divide 250 to both sides. There we go. So now you're going to take $287.50 that you made after 2 years from 250 and divide by 250 to figure out how much you're getting there. To figure out our rate. So that's 1.15. Then we bring down B, which is our initial rate, but we also bring down the 2 years. So that's B squared, okay? So now to get our actual rate every year that it increases, we still have to solve for B. So to solve for B, we have to undo the power 2. And so to undo the power 2, you square root both sides. Right? If it was a 3, you would cube root both sides. If it was a 4, like b to the 4th power, for example, then you would 4th root both sides, right? So whatever it is, you get rid of the power by doing that root. Cool. Okay, so now there we go. So we're going to do square root of 1.15. We're going to go and square root that now. So, oops. So square root 1.15, nice. There it is, we get 1.0723. So B is equal to 1.0723. Nice, probably go 3 decimal places is good. So that's our B value. And so where does our B value go again? Right here. So we take 1.0723 and we put it here for our B value. And then we do 250 again was our initial, so that goes right here. And so they want to know, it says here, if the amount of money at the end of each year increases exponentially, then how much will you have in another 6 years? So I made a mistake here. It's actually not another 6 years. No. It's actually 2 plus 6. It's actually 8 years. And so that's what's going to go there. Cool. Okay, so now we're actually not figuring out how many time or hours it's going to take. It's actually asking you how much will you have after 8 years total. So now you do the 250 times the 1.072, the rate, to the 8th power, or 8 years. And so we go ahead and plug that into our calculator now. So we're going to go 250 times our 1.072, which is our base rate that we figured out, their exponential base rate. And then to the 8th, so that's the caret symbol right there, to the 8th power. That's it, to the 8th power. Boom. So 436. So that's not bad. Woo! Yeah, 250 up to 436. So it's not 379. No, no, no. It's $436. Woo! Awesome. So if we take a look at our notes there and scroll down, let's see here. Okay. So then, yep, that's it. $436. Cool. And then this is just an added thing, so that you don't necessarily have to do. But it was just to, like, they threw this on here just in case you see a problem like this. So then how long would it take for your money to double? And so how long would 250 reach 500? And so you can actually do the 250, 1.072 to the x power. And so to double your money, you set equal to 500, right? Divide by 250. So that would just divide by 250. And so that would just be 2. And then you log base 1.072 on one side, log base 1.072 on the other side, solve for x. And so x would equal about 10 years to double it. So it would take 8 years to get $436, and then to double your money, it'd actually take 10 years. So that was just kind of an added thing there. Cool. Okay, so next, so that's solve for your rates. And then our last step was, now that we have that initial, we could say, like, I don't know, step number 5. And so step number 5 would be use the base rate to solve the question, right? And so that's whether you have to solve for time or solve for, they give you the time and just get the answer, the rate, how much it's grown. And so those are just some steps to try to, help you there. Cool. Okay, so last but not least, we're going to look at the decay form. Now the decay form is exactly the same as the exponential. So it's not like you have to memorize too much more with these different forms here. So the only thing that's going to change is, there we go. The only thing to change is just this b value here. This b value is not going to be greater than 1. And so now we'll go ahead and change that. And so the difference is your b value now, if it lets me change it. So now your b value is going to be less than 1, right? So that's the exponential decay part. So it's going to basically be a negative number, right? Negative number. Cool. So let's give that a try. I think you've got one of those on your homework as well. Let's see here. So Connor bought a new car for $36,000. After 2 years, yeah, there's a car one, I think. After 2 years, the value of the car had depreciated, so it was only worth $29,160. Womp, 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 womp. Yeah, don't buy new cars. If the value of the car each year decreases exponentially, how much will it be after 4 years? Wow. Okay, so we're going to go and do the same thing now. So our initial rate this time is 36,000. And the rate, we don't know how much is decreasing, but we're about to find out. And then after 2 years, it's dropped down to 29,000. Right? 29,000. There we go. Okay, so now it's going to be, not necessarily negative. I don't know. It could be negative, but what's also less than 1? So less than 1 is maybe 0.5, 0.4. So maybe like a fraction, 1/3. So that's still less than 1. I don't know if it's necessarily negative. Maybe I jumped the gun on that one. Sorry about that. Because I'm seeing here this is going to be a fraction, right? And so what's less than 1? Well, a fraction is less than 1. And so we're going to go ahead and divide. There we go. So a fraction can be less than 1. So we're going to go ahead and do 29,160. Awesome. We're going to divide it by 36,000. And so we get 0.81. And so we're going to get 0.81, so b is less than 1. In this case, we divided it over. So we're going to get b squared is equal to 0.81. And so 0.81, cool. Okay, so now we want to square root both sides. And so then b is equal to the square root of 0.81. Don't forget this is a big old fat decimal there, right? So it is less than 1. So now we're going to go ahead and do the square root of 0.81. And so that gives us 0.9. So b is equal to 0.9, and 0.9 is in fact, so that means that b is less than 1 because b is equal to 0.9, and 0.9 is 0.90, which is less than 1. So it is definitely dk. Okay, so that's going to be our initial that we figured out. That's going to be our rate that we figured out. There's our rate. So it's decreasing by 90%, it looks like. Okay, so from there, we've got that. So now we're going to do 36,000, right, our initial. Then we have a rate of 0.9 or 0.90, and, or just 0.9 if you don't want to do 0.90. Okay, so if the car, so you have to be careful and read it. If the value of the car each year decreases exponentially to the nearest dollar, how much will it be worth after another 4 years? So they're not asking for a 2-year value. They're not asking for 4-year value. They're asking for 2 years and then another 4 years. So that's going to be a total of 6 years. Does that make sense? So you're going to have to add those together. It went 2 years, then it went 4 more years. So a total out of 6 years. That was tricky. Tried to trick us there. Yeah, let's double check that. Yeah, so they did it in 6 years in total. Cool. Okay, so now we go and plug that in our calculator. So you're going to go ahead and do 36,000. And then don't forget to do parentheses, because you don't want to do 36,000 to the 6th power. No, no, no. So 0.9, good, to the 6th power. Okay, so then it decreased all the way down to 19,131.88. So 19,131.88. And so that's a big depreciation, huh? After 6 years, your $36,000 car is like cut in half? That's ridiculous. And you're like, but I want to sell it. Oh, you better not worth selling it. So that's DK. That's how DK works. If they ask you to do like, well, how many years would it take, to get to a certain value? This, of course, is time, so you might have to solve for time t, just like we did, you remember, at the very beginning of our video, where we actually had to solve for t. So you might have, and then set it equal to how much it's worth, how many years would it take to depreciate, to, how many years would it take to depreciate to like $5,000, for example, right? And so this is just another example, really quick. And I don't think necessarily, well, you might. Let's try it in our test, in our practice test. So you do your initial, 36,000. And then you do your 0.9. So how long would it depreciate? So let me just write that question. How long would it take to depreciate to only worth, and that's when I buy it, I come along and buy it, $5,000. So let's go and see if it'll, nope, it's not going to let us do that. Okay, so this is just another quick little example, not using the dodo bird, even though that's a fun example of decaying. Okay, so this is just another example. How long would it take to depreciate to $5,000? And if you understand, you can just carry on and don't have to watch this. Otherwise, I highly recommend keep on going. So 0.9, let's say to the t power. So again, this is just another example to help you with decaying with a problem that might come up. And so equals, and so you set equal to 5,000. There's your initial with your base rate 0.9, and then you solve for t. So you go ahead and divide by 36,000 to both sides. Awesome. Oops. Okay, so then we take 5,000 and we divide it by 36,000. Good. We get 0.1388888. So 0.9 to the t power is equal to 0.13888. Cool. And then you want to solve for t. So you have to do what? How do you undo base 9 to the other side? You have to log base 0.9. That's crazy. Log base 0.9 to the other side. So now we'll show you with Desmos, because some of you don't have a graphing calculator, how to plug that into Desmos. That's a crazy one. So, or maybe not even Desmos. Maybe just type in like a log, base calculator. And that's probably just a good idea to try that, because there's lots of websites that do that. So I like to use calculator.net because that's just a pretty nice one. So in this case, we have, let's see here, log bx equals y can be except e. Okay, so we're going to do log base what? So we're going to do log base 0.9. Awesome. So we're going to do log base 0.9. Oops. 0.9. And then of our 0.13888, which is what we got right there, and see what that gives us. And so that gives us 18 years. So you can, that car will last, at least it slows down a little with its decaying there. We'll double check with our graphing calculator real quick. So again, you go to math, you go to log base 0.9 of our 0.13888. And so, it gives us 18.73, so about 18.7 years. Nice. So then t would take 18.7 years. So these weren't as bad as you thought, right? Not as bad as you thought. So you have your 4 problems there that you're going to work on. And so here's our rabbit one. It says increased. And so get started on that one. And so they tell you our initial was 20 rabbits. So that's your initial, right? And then on an island, after 6 months, so there's your time, and it increased all the way to 100. So you don't know what your rate is there, but you do know your time was 6 months. And so you set it equal to, it's increased to 100. And then you remember, you go ahead and solve for your b by dividing 20 to the other side. So 100 divided by 20 is just 5. So now you have b to the 6th power. And then, do you remember how to get rid of that? So this is the crazy one I was talking about. You're going to have to 6th root, right? You're going to have to 6th root both sides. Do you know how to do that? I don't know if I showed you that on the calculator there. So let's show you that. So that's actually the math button. And so it's actually right here where it says X. So it's math button option 5. And so you're going to do option 5. So you're going to do a 6. And then the 5th power, right? 5th power. And so that's going to give us a base rate of 1.307. 1.307. And then they say, how many rabbits will there be at the end of 1 year? Well, we're using 6 as our time. And so we want to know at 12 months, which is 1 year, nice, how many rabbits will there be? So now again, you use your initial, which is 20. Your base, which is 1.037, good. And then to the what power? Well, let's see. So that was 6 months. And so they just want to know, not 6 more years, because that would be 12, but they just say at 1 year, yeah. So we will say at 12 months, what will it be? And so we'll go ahead and plug that. Just helping you with number 1 real quick. Thanks for watching. So we got 20 times 1.037. And then to the, that's the caret symbol, 12th power. I'm going to show you there's calculators that do this on websites as well. Awesome. So 30.929. And I think I messed up somewhere. Let's take a look. So 20 rabbits, 6 months, then rabbits that increase to 100. So then we divide it by 20, we got 5. Then we cube root that. How many rabbits will there be at the end of 1 year? Well, there's our rate. So that's 12 months. So then, let me double check. What's going on there? Okay, so we had 20 to the 1.308. 12 equals y. Good. There's our 12 months. Nice. 1.308, nice. Let's see here. Should be 500. So let's just see what happened here in my calculator. So we had 20 to the 1.3. Oh, made a mistake there. Do you see my mistake? And so I put 1.037. It should be 1.3. Ooh, so I was just trying to go too fast at the end here. So again, we had 1.307. So this should actually be 1.307, but in this case rounds up to 8, so we'll say 8. So be careful that you don't mess up on a decimal, because look what happened. If you mess up on a decimal place, you will get the wrong answer. So be real careful there. Okay, so it's actually supposed to be 1.307 to the 12th power. So now we're going to do 20, and then 1.307. And then that's to the 12th power. There we go. And so that gives us our 496.97. And so then that nice number gets really, really close to, rounds up to D. So number one, the answer is D, which is 500. Nice. There we go. Okay, so then again, last but not least, if you're trying to do a log, you can use calculator.net. So if you're trying to do like an ith root, you know what I mean? You can look for a root calculator, because you can also use the internet for that. Look at that, root calculator. So we were trying to do the 6th root, I believe, is what we were trying to do there. So here's the regular square root symbol. Awesome. Oop, I saw something better. Here's our root calculator on calculator.net again. So calculator.net. And so we're going to do, it was the 6th root, remember, of 5 to get that answer. And so we got, there's our 1.307 that we got. So just Google root calculator and that'll help you get those roots that you need. And so again, kind of deleting some of the stuff we did there so you can see again what we did for number 1. So again, for number 1, we did our base, 20. B, we had to solve for B to the 6th power because it's 6 months, equals our 100 increased to after 6 months. We divided by 20, we got 5. Then we 6th root both sides, we got 1.307. And then we did 20 initial again with 1.307 to the 12th power that gave us nearly 500. Cool. So sorry these videos were kind of long, but just wanted to help you really understand this. So thank you for watching. Fast forwarding time. Thanks for watching. Peace out. Bye for now.